In this video, we're going to discuss logistic regression, a form of regression that's used to model specific data situations that often come up in pretty important examples. Um, you can see this if we're trying to model, say, the probability that someone's going to complete a task on time, or the probability that an individual may have a particular event. Logistic regression is very useful for these types of things, and we'll discuss it. So to start, we're going to start with a review of some basic concepts that we expect that you've seen before this class. We're going to discuss some context of where we are actually talking about this particular model. We're going to discuss the model itself. We're going to discuss interpretation of the model, which is a huge component in logistic regression. We're going to discuss the model usage and how we can apply it. Then we're going to discuss some of the details of logistic regression, going in depth on a few of the different components that may be involved here that are not involved elsewhere. Finally, in a future video, we'll discuss the utilization of software for logistic regression. Beginning our review, we start the review talking about odds. If you're not familiar with odds, odds are a way of quantifying probability or likelihood. Probability is its own way of quantifying probability, but odds are a different way to quantify probability. Commonly used in gambling. I'm not much of a gambler personally, but the main place that I see odds used professionally is in logistic regression. In fact, one of the only times I see odds used more than probability is in the context of logistic regression. As far as I'm concerned, it's one of the only reasons odds and odds ratios are still part of any academic discussion. Now, odds are not simply the probability of an event. That's probability. Odds are the probability of an event divided by the probability of the event not happening. So if I'm looking at this, O stands for odds, E stands for event, and P stands for probability. So I would read this equation as the odds of the event is equal to the probability of the event divided by 1 minus the probability of the event. Now that denominator, that thing on the bottom of the division, 1 minus probability of the event, is the probability of the event not happening. So you can also look at this as P of E on the top, probability of the event, divided by probability of not the event. And again, that's just 1 minus P of E. Stepping away from probability, we can calculate this via number of successes and failures. So maybe number of S successes divided by number of failures. I should note here, P of E, I use this as kind of mathematical notation, but P of E is often written as P for probability or even pi, which weirdly stands for probability, not 3.14159 in statistics. You'll sometimes see pi used as a representation of probability. So don't be surprised if you start seeing P of E as the probability of an event written as P in this class. So just be aware that that's going to come down the pike. What value can odds take? Well, this is a great time to pause the video and give a shot. Plug in a couple of probabilities. You know probability ranges from 0 to 1. Plug in a couple of probabilities on the low end and a couple of probabilities on the high end of the probability range to check out what the odds are if you want to. So I'll give you a second to pause the video, and then you can come back if you want to try it. Or if you don't want to try it, don't pause the video and wait a second, and we'll talk about it then. Coming back to this, the probability, when it's very low, the odds is going to be very low, all the way down to potentially 0. If the probability is 0, we get 0 divided by 1 equals 0. The probability is very large. We get very, very large odds all the way up to infinity. Not equaling infinity, but approaching infinity. So odds ranges from 0 to infinity. Now the trick is, with odds, that there are two ways to discuss the meaning of that. So if I'm talking about one machine failure and 1,000 working machines, I might plug in the event being failure. I would calculate the odds out to be 1, the failure, divided by 1,000 the working machines, and the odds in that particular case would be 1 over 1,000 or 0.0001. In the case of excuse me, 0.001. In the case of looking at the odds of the machines working, I would do 1,000 working machines divided by 1 failure. That odds would be 1,000. And I mention this because the way in which you phrase it as failure versus success, or as which case are you considering? Are you trying to model when they fail, or are you trying to model when they work? That can have drastic impacts on your interpretation of your equation. That is, the interpretation is so dependent on which way you code your dependent variable and your independent variable. And it's important to consider these things. So again, the 0.001 and the 1,000 are both potentially parameters in a model, and they both represent the same thing: 1 machine failure and 1,000 working machines. But one looks very, very small, one looks very, very large, and in certain contexts, we may prefer the large representation or the small representation. And again, it's important to realize these are two equally valid expressions. They both mean the same thing. It just depends on which way I'm phrasing it and which way I've coded my variables. So again, I can have a parameter estimate of 1,000 representing the working machines to the non-working machines. I can have a parameter estimate of 0.001 representing the non-working machines to the working machines. And again, it's just the way in which that's phrased. What is comparing to what can make a huge difference in the size of my parameter estimates. And because of this, looking at a small number versus a large number, smaller numbers aren't always worse in odds. Sometimes, again, that 0.001 represents just as extreme of a relationship between failure and working as 1,000. So the size is a bit asymmetrical, and it's important to realize that within odds. So in reviewing regression, recall that in regression we have a continuous dependent variable, and we can use a variety of different independent variable options. We could use continuous, we can use categorical independent variables. We're looking to predict or explain the dependent variable with some linear combination of our independent variables. And checking out a data set below, we have miles per gallon, number of cylinders, displacement horsepower. I have no idea what DRAT is, to be quite honest with you. Weight, quarter of a mile times seconds. All of these are different components as related to different cars that were captured within the Motor Trend Car Road Test circa 1974. So in this, let's say I'm trying to predict miles per gallon. This is a great dependent variable for our classic normal regression because miles per gallon is a continuous variable. Now I can predict this using a variety of different independent variables. I could have number of cylinders, engine displacement, but note on the right, I can also have AM, which stands for automatic manual. I can have categorical independent variables, category, automatic or manual control that relates to my dependent variable. So my independent variables can be continuous and categorical. It's the dependent variable that has to be continuous within my classic regression. Now I know the data situation, that's what we just described, but let's talk about the model. So the model can be written as, on the left-hand side, the outcome variable, in our case with the previous data set in miles per gallon, is represented by a linear combination of x1, x2, x3, that'd be the weight, the automatic manual, etc., where the beta 0 is the intercept. When all the independent variables are 0, what is the predicted value of the dependent variable? And then all of the different slopes of the relationship between the independent variables and the dependent variable, and we'll go a bit more in depth on this interpretation as we discuss the interpretation within logistic regression. But this is something to consider, these interpretations based on your previous classes in regression. And of course, E is the error term. Incidentally, we aren't going to have E as the error term in this class for some technical reasons, which we will reference but not go in depth on. All right. So now let's look at the output of that model from some software. As we're looking through this, consider How do we read each of the parameters? How do we interpret each of the parameters within an appropriate context? So looking through this, the very, very, very first thing I look at in the output is the right-hand side. That's the p-value. Well, typically, the very first thing I'd look at is the model assumptions and make sure that the model passes all of its assumption checks. That is, we don't have any big red flags in things that we're assuming to fit the regression model that prevent us from being able to interpret the parameter estimates. But when looking at the parameter estimates, the very first thing I look at is, as long as there aren't any interactions or anything crazy, is the p-values. So within these p-values, I look at the p-values because the p-values are what's going to ultimately indicate which of the relationships are supported for the population, not just for the sample. That is, I took a sample of cars. I want to see which of the relationships with the independent variables affect miles per gallon in the population, not just in my sample. What do I have evidence for that's effective in the population? So looking at these, we only interpret the parameters that we have evidence for in the population, because interpreting parameters that we don't have evidence for in the population implies that there is a relationship, when again, we don't have evidence of any relationship in the population for anything where the p is of a sufficient size. In a classic case, we use p greater than 0.05. In this particular case, the only one that we have as statistically significant is weight. So this is the only one that I would say I have evidence for that there's a relationship between weight and miles per gallon in the population. For the weight estimate, -4, this indicates that as weight increases by 1, we expect the miles per gallon to go down by 4 after accounting for all of the other variables in the model. Now this might sound drastic, and it is quite drastic. Weight is in thousands of pounds. So weight increasing by 1 is actually the weight of the vehicle increasing by 1,000 pounds, and that has a very large impact on the nature of the estimate. It's worth noting, and this is a bit of a review, but if we had typed in weight in terms of single pounds instead of thousands of pounds, while the estimate would have changed, the standard error also would have changed. The t-value, that is our test statistic, would not have changed, and the p-value, that is our p-value, would also not have changed. So it's important to realize what changing the scale of your independent variable does in terms of your output. It would change our interpretation. In this case, we interpret it as when weight increases by 1,000 pounds, miles per gallon drops by an average of 4 miles per gallon, all other variables being controlled for. But this comes from, again, the scale of weight. It does not, the scale of weight, while it affects the interpretation, does not affect the statistical significance. This is actually an important point that we'll discuss later, and the reason is because being able to change the scale of something like weight is very, very important. Let me rephrase this. If weight were written in single pounds, the parameter estimate here wouldn't be -4, it would be -0.004, which actually would round to 0 when I rounded 2 decimal places. Now that doesn't mean it's any less impactful. In fact, again, the statistical significance and the t-value are going to be exactly the same, but the interpretation will change because I would move up move down 0.004 miles per gallon for every pound that the car changed. It's very useful sometimes to rephrase your independent variables in terms of a scale numerically that actually has a more intuitive interpretation for your parameter estimate. In this case, a weight change of 1,000 pounds is a lot but reasonable, and saying if you add 1,000 pounds to the car, you're going to lose 4 miles per gallon, all other things being considered, can be a very useful interpretation. So realize that changing the scale of those independent variables is an important tool in our toolbox, and it's something we'll demonstrate later. So quickly, I want to place the discussion of this lecture within the broader discussion of our classic inferential options. Our classic inferential options, we have independent variables and dependent variables. We have continuous and categorical variables. And again, classic options, if we had a categorical dependent variable and a categorical independent variable, we would use a chi-squared. If we had a continuous dependent variable and a continuous independent variable, we would use a regression. If we had a continuous dependent variable and a categorical independent variable, we would use ANOVA. And when we have a categorical dependent variable and we want to use a continuous independent variable or a mix of continuous and categorical independent variables, we use logistic regression, which is going to be the focus of this particular lecture. Let's talk about some context to the logistic regression. The goal and the method of logistic regression are really the same as normal regression. The big change that's probably the most obvious is that logistic regression is a tool we use with binary outcomes or categorical outcomes with two possibilities. There are options for categorical outcomes with more than two possibilities. It'll be referenced in this lecture, but they are beyond the scope of what we're going to discuss in this class. Now consider, what if we used regular regression with a binary outcome, 0, 1? Well, we're going to violate some of our assumptions. Certainly normality, model fit, homogeneity of variance. We probably are going to violate every assumption, linearity, every assumption that we have within the model. These are called linear probability models, actually, when you just do it anyway. And there's a fair amount of reason that we want to avoid that in certain situations. There's a few situations where these violations are not as impactful, but typically it's considered bad practice in the statistical community to run a binary outcome as a continuous outcome in a typical regression because, again, assumptions are so badly violated. The other reason we may want to avoid this is because we predict very poorly. Regular regression's outcome varies between negative infinity and positive infinity, whereas if we give it a binary variable, the only possibilities are 0 and 1. We might then predict 100,000 when our top prediction out should be 1, or we might predict negative 30 when our lowest prediction out should be 0. So that invites some questions as to how we then interpret and quantify and find meaning in the output of the model, and it can introduce some difficulties. So what can we do within this context? What are our tools? Well, the goal is to go from 0, 1 to a full range of regression that is negative infinity and positive infinity. And we've already talked about one of the tools that can get us halfway, that is using odds. But we need something else to help us go the rest of the way. And this, broadly speaking, is called the logit function. It's going to incorporate some odds, but it's going to add a logarithm which allows us to go not just from 0, 1 to 0 to infinity, which is what probability to odds lets us do, but adding in the log lets us go from 0 infinity to negative infinity to positive infinity. And so the combination of log and odds is the logit function, and sometimes you'll hear this called the log odds, literally meaning the log of the odds. Again, ultimately, this accomplishes our goal. It allows us to take our binary variable and map it to something that's the true outcome of regression, something that's between negative infinity and positive infinity. Now, the inverse of this function is really going to be necessary in a moment. So it'll feel kind of silly that I'm just giving this right now, but it's worth saying that to take the inverse logit of whatever I want to find the inverse logit of, I take exp of the number divided by 1 minus exp in the number, or 1 plus exp in the number, excuse me. The exp of x is just an e, that's a number, 2.7184814, to the, so this is e to the x power, and that is the opposite of the natural log, which is our transformation. So I would take e to the x power, and that'll cancel out my log. And I see that in writing log, traditionally we were at log to be base 10, and we use ln for natural log. But when I'm writing log here, please take that as the natural log, so my e to the cancels it out. I apologize for the mix in notation. All right, so now that we've mapped this 0, 1 to something with a full range of negative infinity to positive infinity, we can look at our regression model. And you'll note that the regression model is the same thing on the right-hand side as our traditional regression model. And I hope this is a bit expected because, again, this transformation that we did on the left with the probability was to get it so that our regular regression could model this probability. P is the probability of success. That is the probability that the dependent variable equals 1. Beta 0 is still the intercept. That is, it's the value of the left-hand side of the equation, the log odds of the probability, when all of the other variables are 0, all the other infinite variables are 0. And beta 1 is the slope, in a sense, of each of the independent variables. Now, I say slope in a sense because this slope is not particularly meaningful. It's the slope. It measures the relationship as the independent variable increases by 1 in the change of the logit of P, or the change in the log odds of P. And that's true. That's a true interpretation, but that interpretation doesn't actually mean much when we end up trying to use it. All right. So again, the interpretations of the parameters don't mean a ton when we try to use them. Typically, what we'll end up doing, and there's a middle ground here, but is to reverse our transformation of the probability once we have our parameter estimates to find the probability. Now, this equation looks yucky because it is yucky, but in this case, this is how we would reverse the regression equation to get P by itself in terms of our parameter estimates. And again, note this exp with all this stuff in it is just e to this. So all of the stuff in the parentheses there is in the power of e. We typically use this form for fitting the model, but this form can be really handy when we're trying to interpret the parameters once the model's fit. Again, because instead of having the parameters refer to the log odds of P, we now have the parameters referring to P itself, the probability. Let's look at some logistic regression output for a hypothetical case. Let's say in this particular case, we're going to try to predict if an employee is on time using as predictors if they're classified as a good worker versus not a good worker, and rating on their collegiality. It's just a collegiality index. It's a continuous variable. So good worker, not good worker. It's an independent variable that's categorical, 2 options, and collegiality is a continuous variable, and we're trying to predict if they're going to do the project on time. So consider what the below output. Is it good? Is it bad? How do you know? And then consider what you would typically interpret this output to say. So looking through this, we might start with the p-value just like before. We'd say collegiality is the only statistically significant variable related to whether or not a person's going to be on time after accounting for if they're a good worker or not. In this particular case, good worker, for good workers, 0.78. If I were trying to interpret this in classic regression way, I'd say for good workers, the log odds increases by 0.78 for being a good worker, of being on time. The log odds of being on time increases by 0.78 for being a good worker. For collegiality, the log odds of being on time goes up by 3.18 for every point increase on the collegiality scale. And again, what I hope you're hearing in this is when I'm quote unquote interpreting this, I'm saying things like this is how much the log odds of being on time increases. I'm not saying this is how much the probability of being on time increases or even the odds of being on time increases. So this is a difficult interpretation and quite frankly is not intuitive at all. So we really need to take a step back when we're looking at this and consider, go back to the chalkboard as it were, to refocus on the interpretation of logistic regression because of what you see on the left-hand side of the equation, the fact that we're not predicting probability, we're predicting the log of the odds of the outcome. So back to the drawing board. For technical reasons, and by technical reasons I mean the monotonically increasing transformation, the interpretation of the sign and significance is actually pretty straightforward. That is, I can read through the output and interpret the sign and significance in a way that I typically would. Significance still indicates whether or not I believe that there's a relationship between the independent variable and dependent variable in the broader population. That is, do I feel that I have evidence that this relationship would be reflected in the broader population. That's where our statistical significance comes into play. And the sign still indicates the direction of the relationship. That is, a positive sign would indicate that as my independent variable increases, the probability of the outcome increases. Probability of the outcome of 1 increases. So again, it depends on how you code. And a negative sign would indicate that as my independent variable increases, the probability of the outcome decreases. So positive, they both go up. Negative, as the independent variable goes up, the probability goes down. And again, these are can both be interpreted in terms of probability. So significance, probability is related. Sign, we can interpret probabilistically. The real challenge, though, is interpreting the quantity or the magnitude. That is, when the parameter says 3.18, can I say 3 times more likely? Like it's positive, so I can say as collegiality goes up, the probability of being on time goes up. But by how much is the question? I can say it's statistically significantly different than 0. So I believe that it's happening in the broader population. But the question is by how much? That quantity part is really difficult here, even though the significance and sign is a little bit more straightforward. So the real challenge here is for a couple of different reasons. First, the coefficients are multiplicatively related to the probability and odds. And this is because of our transformations and ultimately the reverse transformation that has to happen to get us there. But that multiplicative relationship can introduce some difficulties in the interpretation. Secondly, it's because transformations are needed to even begin interpreting. That is, I can't even approach the interpretation of quantity or magnitude until I've done some transformations. And even after doing the transformations, the interpretations of quantity and magnitude are not straightforward. Let's revisit the output now and solely consider significance and sign. So first, let's consider which variables we're even confident in our evidence for. And again, we start with the p-value here. I'm not really confident there's even a relationship between being a good worker or not a good worker and whether or not you turn in your work on time after accounting for collegiality. And it's important to include that caveat after accounting for whatever other variables in the model, because that can have a very meaningful impact in the way in which we interpret our parameters. That said, I am pretty confident or confident enough in my relationship between collegiality and whether or not you turned in the project on time after accounting for being a good worker or not. So collegiality is probably the one I would focus on here. I'll practice interpreting both so that we get the practice. But if I'm interpreting this quote unquote for real, then I would focus primarily on collegiality. So again, significance aside, I'm not going to worry about that right now. Let's consider relationship between the independent variables and the outcome. So we just talked about significance. Now let's talk about sign. Sign for good worker. Good worker is 1 for good workers and 0 for bad. So when I go from 0 to 1, that is increase, become a good worker in comparison to not good workers, my probability of turning in work on time is increased. That's the sign here. Positive sign, higher likelihood of being a 1 in the dependent variable, that's turning in my work on time, when there's an increase in the independent variable. That is, I go from 0, not good worker, to 1, good worker. How much is that? Well, we haven't really talked about magnitude yet. Again, that's a difficulty. So the quantity, that's something we can't really interpret yet, but I can say, again, significance aside, when being a good worker in comparison to not a good worker, higher probability of turning in things on time. Collegiality, same way. When I increase by 1 in the collegiality scale, I have a positive increase in the probability that I turn in my work on time. Is that 3 times the probability of turning in my work on time? No, it's not. Again, the magnitude we can't interpret. We can just interpret the sign and the statistical significance. We do believe there's a relationship after accounting for if the person's a good worker or not, and we believe the relationship's positive. That is, I believe that as collegiality increases, the probability of turning in your work on time increases. All right, so we're going to get to parameter magnitude interpretation, but first, let's talk about the very basics of how we use the model. And to do that, I really want to take a step back on the complexity of the model and really just look at one variable. And we're just going to remove collegiality for a moment and just look at good worker, yes or no, and completed on time, yes or no. The first things I want to point out here is the coefficient for good worker, 2.53. This is very different than the coefficient in the previous slide. And this is so important to acknowledge, is that when we account for other variables, the interpretation drastically changes. And what that means is when I'm interpreting an independent variable, when there are other covariates in the model, it is very important within my interpretation of one variable to acknowledge that the other variables are in the model. Because if the other variables weren't in the model, the parameter estimate for the coefficient I'm interpreting could be very, very, very different. That is, in the previous model, I would say the effect of good worker on turning in a project on time after accounting for collegiality. And that last part is so important because in this model we see the effect of being a good worker on turning in your work on time is very different if I'm just looking at the good worker part. The good worker part after accounting for collegiality is a very different estimate than the worker part that doesn't consider collegiality at all. And you may be surprised at the degree of change that this has. Again, very interesting implications. I'll leave it there for now, but just consider the importance. Okay, so right now we have the coefficients as they're additively related to the log odds. That is the log, and then inside the parentheses is the odds. But we could get this to reference just the odds, and that's by canceling out the log. So how we cancel out a log is we set both sides of the equation as a power of e. So I put both sides as a power of e, this exp, just think about a little e as the base and then a little up arrow and then everything inside the parentheses is in the exponent. Here I'll show you on the right-hand side. Now the e to the cancels out log and leaves us with just the odds on the left side. And in the right-hand side, we're left with e to the everything on the right-hand side. Now, if I split up the plus sign in a power, and you may or may not remember this from algebra, but splitting up a plus sign in a power is the same as multiplying two things with the same base together. And I really need to say here, again, the effect is multiplicative, and this is what that means, is that instead of adding two different numbers together, when x changes, we multiply two different numbers together when x changes, and it has a drastic change in the way that we interpret our parameters in comparison with traditional regression. So from here, we can see a much more useful form of the parameters. That is, now I have parameters that are talking about the odds, not the log odds, whatever those are. And so parameters that talk about the log, or excuse me, that talk about the odds actually can be interpreted with regard to the odds directly. So that's why people like interpreting with regards to odds, is it's a pretty quick change. I just put the stuff in the equation. I put e as the base, and I put those numbers as the power. And then I can write my interpretation in terms of odds. Now, one of my favorite tricks in dealing with things like logistic regression is to plug in a couple of numbers for a couple of different cases. And that really helps me to make an interpretation. If I'm dealing with a bunch of independent variables, I'll set all of the other independent variables to equal something, usually their average value or something like that. And then I'll just change one at a time to see what's the effect that it has on the odds or even the probability. And then I can use that to come up with an intuitive understanding of how that variable impacts the probability. In this case, let's try plugging in a couple of numbers for x, that is whether the person's a good worker or not, good worker being 1, not good worker being 0, and seeing what the outcomes are in terms of the odds. So for a not good worker, plugging in x equals 0, and on the left-hand side, this is solving for odds. I literally plug in the value 0 for x and type it into my calculator. Typing this in, that right-hand side, e to the 2.53 times 0, works out to be 1. So I get the left-hand side, e to the negative 1.32, times the right-hand side, which is 1, ultimately leaving me with just the left-hand side, e to the negative 1.32, which is 0.2671. Now, we really want to interpret this as something like the probability that a not good worker turns the project in on time is 26.7%. And again, it is very difficult because this is how we want to interpret it, but it's really not the way we should interpret it. We really should be interpreting this as the odds of turning in on time are 0.2671 for every one time that we don't turn it in on time. And again, that's a rather complex interpretation, but I'll say it again. The odds of turning it in on time are 0.2671 for on time to 1 not on time. So for every 2.671 times we turn it in on time, we'd expect to turn it in once not on time. For a good worker, I do the same thing, except instead of plugging in x equals 0, I plug in x equals 1. And this is just how I coded my independent variable good worker, 1 for the good workers and 0 for the not good workers. And then I go in and calculate my odds. Now, when I plug it in, the left-hand side is still 0.2671. That's the e to the negative 1.32. Now, the right-hand side doesn't disappear. The right-hand side works out to be 12.5535. Working this out, the odds of a good worker turning this on time are 3.3530. That is to say, interpreting this, the odds of an on-time completion for a good worker are 3.530 to 1, or for every 3.3530 times we turn it in on time, we'd expect 1 time to not turn it in on time. I should mention here, because we fit a logistic regression model to this data, these are predicted odds. That is, this is how we're predicting the odds after doing our model on the data. This isn't necessarily the exact correct odds for what match with the data set. That is, we're not calculating this from our data, we're calculating this from our predicted model. And our predicted model might not predict with 100% accuracy, in which case our predicted values here might not perfectly match what the data are showing. Again, the goal is to come up with a model that predicts well. So realize that that's a potential that if we don't have an absolutely perfect model, these odds may not perfectly match what we see in the observed data. All right. Now that we have basic model usage, let's go back to what we were talking about in interpreting the size of the number, the magnitude. So again, we said we can do significance and sign pretty easily, but the quantity, that's the hard one. So let's talk about the magnitude or quantity right now that we've talked about how we calculate these odds. Consider the example we worked through, the good workers effect on odds. So remember the left-hand side, the 0.2671, that was there when the not good worker was there too, and that's there when the good worker's there. But the good worker, the new thing that being a good worker adds, is that you take that baseline level of odds and you multiply it by 12.5535. So there is a multiplicative increase in the odds because you're a good worker of 12. You are 12 times the odds of a bad worker to do your work on time. Now, in this particular case, again, it's important to realize the effect was multiplicative, and this is a weird one. If we took this odds listed right here, the one that's listed here with the black and red is the odds of the good worker. The odds of a bad worker is just the stuff listed in black, and we divided them. We put the odds of the good worker divided by the odds of the bad worker. The 0.2671s would cancel out. We would be left with the stuff in red, 12.5535. Why is this a thing? This is a thing because in general, this is the effect of our parameter estimate. When we take those betas and we put them as a power of E, what we are calculating is actually the ratio of being 1 versus being 0, or being 1 more versus being 1 less in the case of a continuous variable, which we call ultimately the odds ratio. It's the ratio of two different sets of odds for two different situations. In our particular case, 12.5535 is the ratio of the odds of being a good worker divided by the odds of being a bad worker, or the multiplicative increase that being a good worker has on your odds over being a bad worker. Now, the odds ratio can have any value between 0 and infinity, just like odds. The odds ratio is a little different than maybe you would normally think. An odds ratio of 1 represents no effect. So when I have all of my e to the betas, if I'm looking at that, my exponentiated betas to interpret their odds ratio interpretations, a 1 represents no effect rather than a 0. Values above 1 can be interpreted as the increase in odds over the comparison. So we take that odds ratio, we subtract 1, and that's the percentage increase in odds. So for instance, let's say we had the effect of a female on some kind of an outcome, and our odds ratio was 1.82 for the variable female, where 1 is a female and 0 is a male. We could interpret this as the odds of the outcome are 82% higher for females than males, or 82% of females to males. For binary independent variables, it's convenient to code such that the odds ratio is bigger than 1. I write this in. This is something that's talked about potentially in some of your readings or textbooks. It is convenient to do this when you don't have anything else to do or anything else to guide your coding. For me, though, if I'm looking at an independent variable of meaningful interest, I might code in a way, depending on the variable, that matches the situation. So for instance, if I'm looking at, say, a treatment and control, I would always leave the treatment coded as 1 and the control coded as 0, even if the direction of the odds changed. Now, for something like sex of a participant, female, male, I might code it in this way because the decision between which direction to code it isn't particularly implied unless I have an explicit reference group. Let's say males had to be the reference group or females had to be, in which case I would leave it as what theory recommends. But when I don't have a better way to code things, it is convenient to code them such that the odds ratio is greater than 1. The reason is because the interpretation that the odds of the outcome are 82% higher for females and males is true. If I had reverse coded that, the odds ratio would be 0.5495, but the above interpretation of the odds of being dv equals 1 are 82% higher for females than males is actually still true, even though the odds ratio is 0.5495. So it eliminates some of the confusion in that particular case. You can always just say, instead of interpreting as a percent increase, you can always just say, let's say in this particular case, that the odds of females, the dependent variable, are 1.82 times the odds of the dependent variable with males. So you can always go back to that base level interpretation, and you don't have to use this percent increase language or even this concept. So just like with odds ratios are so easy to interpret inappropriately. Odds ratios are incorrectly very often interpreted as ratios of probabilities. These are actually called relative risk or risk ratios. There's some ways to calculate them from odds ratios. This is an open discussion debate on if that's appropriate or when you should use it or why you should use it. I disagree a bit with maybe some of the things our readings have said, in that I think relative risk is always more useful than odds ratios. But there are some common reasons why that transformation from an odds ratio to a relative risk is not always straightforward. So for instance, the incorrect interpretation of an odds ratio is good workers are 12.6 more likely to be on time than bad workers. And the reason that this is incorrect is because of the phrase more likely. That involves probability or likelihood, and we are not discussing probability or likelihood. Odds ratios are discussing exactly what they say, a ratio of odds. So the correct interpretation for these numbers would be good workers have 12.6 times the odds of being on time as bad workers, or 1,160% times the odds of being on time as bad workers, if you wanted to use the percent conversation from previously. Again, often with our parameter estimates, especially when they're large, this interpretation that's on the board right now is a little bit more convenient. All right. So now that we have discussed all of the things that we've discussed, let's revisit our sample. So let's head to these estimates and look at the parameter estimates. Now, it's important to realize these are not odds ratios. These are not odds ratios. These are the betas as are related to the log odds. Remember, to get to the odds ratios, we have to place these as a power of E. So to do this, let's say we're going to do this for good worker, and I would take the 0.78 and raise it as a power of E and work that out on my calculator. I get 2.18. And the interpretation would then be good workers have 2.18 times the odds, or the odds of a good worker being on time compared to a not worker is 2.8 times those odds after accounting for collegiality. Now, the important thing here is times the odds. Again, we're not talking about likelihood. We're not talking about probability. We're talking about times the odds. And again, this is something that many people, many smart people mess up very often. Now, there is a caveat. Let me lawyer up here. I understand the p-value for a good worker is 0.48, so it would actually be incorrect to include this interpretation in, because I don't have evidence that this is actually any different, that being a good worker versus not a good worker is related to the outcome of turning in work on time in any way. I don't have evidence for that within the population, so I would not write this interpretation because, again, it's not supported with my analysis or through my data, because that p-value is so high. But it is good practice to practice how we would interpret that, so please take it in that context. All right, let's try collegiality. So for collegiality, we take E and we put 3.18 as the power of E. We get 24.05. So for a one higher on the collegiality index, we have 24 times the odds of turning in your work on time in comparison with the workers who are not one higher. Now, this is statistically significant. We believe that this relationship is true within the population. But I want you to consider something, and that is, what does one higher actually mean? And in this particular case, I actually think collegiality is all between 2 and 2.5. So it's actually impossible to be one higher. Maybe what we should do in this particular case is we should change the scale of collegiality to maybe be a tenth higher, which, from 2 to 2.5, that a tenth is a meaningful movement for whoever looks at the collegiality scale and interprets that. But that way, this interpretation of collegiality would be a lot more appropriate, because right now, this 24 times the time is talking about an unrealistic increase. That is an increase of 1 on the collegiality scale. When all values are between 2 and 2.5, an increase of 1 on that scale is impossible. So yes, if you increased an impossible amount, you would have a 24 times higher odds of being on time. But again, within the scale, within the context, it's impossible. This would suggest we rescale the variable. All right, so this has been a discussion of some of the basics and diving a little bit into logistic regression. We will pick up in the next video on going a little bit more into the weeds on logistic regression, focusing on some of the different components, some of the different details that come up when implementing these types of models.